You sit in a room, surrounded by objects you assume are solid. The chair beneath you, the walls around you, the floor supporting your weight. You reach out and touch the surface of a table, feeling its apparent hardness, its seeming permanence. This experience feels undeniably real, unquestionably concrete. Yet if you could somehow zoom into that table with impossible precision, past the level of molecules, past atoms, past even the nucleus, you would find something that challenges the very foundation of what you just experienced. You would find that the table is almost entirely empty space, held together by forces that exist in a realm where particles can be in multiple places simultaneously, where the act of looking changes what you see, and where the basic building blocks of reality refuse to behave like the solid, predictable objects of everyday experience. This isn't merely a curious footnote about the microscopic world. It points to something far more unsettling. The reality we experience directly through our senses operates according to one set of rules, while the reality revealed by our most successful scientific theories operates according to an entirely different set. And the question of how these two realities connect, how the solid world of experience emerges from the probabilistic quantum realm, remains one of the most profound puzzles in science. It's a question that sits at the intersection of physics, philosophy, and consciousness itself. For nearly a century, physicists have developed quantum mechanics into one of the most precisely tested theories in the history of science. It predicts the behavior of subatomic particles with extraordinary accuracy, enables the technology that powers our modern world, and has never failed an experimental test. Yet despite this remarkable success, quantum mechanics presents us with a picture of reality that seems fundamentally incompatible with our direct experience. The theory suggests that particles exist in multiple states simultaneously until they are measured, that distant particles can instantaneously influence each other, and that the boundary between observer and observed becomes mysteriously blurred. The heart of this puzzle lies in what physicists call the measurement problem. In the quantum world, a particle doesn't have definite properties like position or momentum until someone or something measures it. Before measurement, the particle exists in what's called a superposition, a ghostly combination of all possible states. But the moment a measurement occurs, this superposition collapses, and the particle suddenly acquires definite properties. The mathematics of quantum mechanics describes this process with perfect precision, yet it offers no clear explanation for why or how this collapse occurs. Consider the famous thought experiment of Schrödinger's cat. A cat sits in a sealed box with a device that has a 50% chance of releasing poison based on the decay of a radioactive atom. According to quantum mechanics, before we open the box, the radioactive atom exists in a superposition of decayed and not decayed states. This means the cat should also exist in a superposition of alive and dead states. Yet when we open the box, we always find either a living cat or a dead cat, never something in between. The theory perfectly predicts the probabilities of what we'll find, but it doesn't explain how the definite outcome emerges from the indefinite quantum state. This puzzle becomes even more perplexing when we consider that measurement devices themselves are made of quantum particles. If a particle detector is composed of atoms that obey quantum mechanics, then shouldn't the detector also exist in superposition until it too is measured by another device? And wouldn't that device also need to be measured by yet another device? This leads to an infinite regress that seems to have no natural stopping point within the framework of quantum mechanics itself. Some physicists have proposed that consciousness plays a special role in collapsing quantum superpositions. In this view, the subjective experience of observation is what transforms quantum possibilities into classical reality. But this suggestion raises as many questions as it answers. What exactly constitutes consciousness? Does a mouse collapse quantum states? What about a bacterium or a computer? And if consciousness is required for quantum collapse, how do we explain the existence of a definite classical world before conscious observers evolved? Other interpretations attempt to avoid the measurement problem entirely. The many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur, but in separate parallel universes. When you measure a particle's position, the universe splits into multiple branches, each containing a different outcome. You experience only one branch, but all the others exist just as real as yours. This interpretation preserves the mathematics of quantum mechanics without requiring any mysterious collapse, but at the cost of populating reality with an infinite number of unobservable parallel worlds. The pilot wave theory takes a different approach, proposing that particles always have definite positions and momenta, but they're guided by a quantum field that we cannot directly observe. This hidden reality determines the outcomes of measurements, while preserving the probabilistic predictions of quantum mechanics. Yet this interpretation requires accepting the existence of instantaneous influences across vast distances and abandons the principle that physics should only deal with observable quantities. Each of these interpretations addresses some aspects of the measurement problem while introducing new puzzles of their own. The persistence of this fundamental disagreement among physicists reveals something profound about the limits of scientific explanation. We have a theory that works with unprecedented precision, yet we cannot agree on what it tells us about the nature of reality itself. The measurement problem becomes even more acute when we consider recent experiments that push the boundaries between quantum and classical behaviour. Physicists have succeeded in creating quantum superpositions of increasingly large objects, from individual atoms to small molecules to tiny mechanical oscillators. These experiments suggest that there may be no fundamental size limit to quantum effects, no natural boundary where the quantum world gives way to the classical world we experience. Yet somewhere in the transition from microscopic to macroscopic, quantum superpositions seem to disappear and definite classical properties emerge. The process responsible for this transition, called decoherence, occurs when a quantum system becomes entangled with its environment. The delicate quantum coherence that allows for superpositions is rapidly destroyed by interactions with surrounding particles, effectively hiding quantum effects from our direct observation. But decoherence alone doesn't solve the measurement problem. It explains why we don't observe macroscopic superpositions in practice. But it doesn't explain why measurements yield definite outcomes rather than leaving us with an entangled mess of observer and observed. The mathematics of decoherence still describes a world where all possible outcomes exist simultaneously, even if they're hidden from our perception. This brings us to one of the most unsettling implications of quantum mechanics. If the theory is taken at face value, without additional assumptions about measurement or interpretation, some physicists have suggested that aspects of reality may be relational rather than strictly observer-independent. Different observers measuring the same quantum system at different times or in different ways might experience genuinely different realities. What we take to be objective facts about the world might actually be observer-dependent features of our particular measurement interactions. The philosopher Hilary Putnam once argued that we might be nothing more than brains in vats, fed sensory experiences by some external computer, with no way to determine whether our perceived reality corresponds to anything outside our own minds. The measurement problem in quantum mechanics suggests an even more radical possibility. Perhaps the idea of a single, fully observer-independent description of reality may be more difficult to sustain at fundamental scales. Perhaps reality is always and necessarily a collaboration between observer and observed, with no meaningful distinction between the two. This possibility challenges our most basic assumptions about the nature of scientific knowledge. Science has traditionally been viewed as the enterprise of discovering objective truths about a reality that exists independently of our observations. But if quantum mechanics is correct, then the act of observation might be an irreducible part of reality itself, not merely a tool for discovering pre-existing facts. The implications extend far beyond physics into questions about consciousness, free will, and the relationship between mind and matter. If observers play a fundamental role in determining the properties of physical systems, then consciousness might be woven into the fabric of reality in ways we're only beginning to understand. The hard problem of consciousness, the question of how subjective experience arises from objective physical processes, becomes even more perplexing if the physical world itself depends on subjective observation. These questions remain as puzzling today as they were when quantum mechanics was first developed nearly a century ago. Despite decades of experimental progress and theoretical refinement, we seem no closer to resolving the fundamental tension between the quantum description of reality and our classical experience of it. The mathematical formalism of quantum mechanics continues to make incredibly accurate predictions, but the question of what it all means remains as mysterious as ever. And perhaps the most unsettling part is not that we don't have the answer, but that the question keeps surviving every explanation we invent. This persistence points to something deeper than mere ignorance or incomplete data. It suggests that certain aspects of reality might be fundamentally beyond the reach of empirical investigation, not because our instruments are inadequate, but because the questions themselves exist at the boundary where measurement becomes impossible. Consider what happens when we try to measure anything with absolute precision. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This isn't a limitation of our measuring devices, but a fundamental feature of reality itself. The very act of measurement disturbs the system being measured, creating an irreducible uncertainty that no amount of technological advancement can eliminate. But this limitation runs deeper than the uncertainty principle suggests. Every measurement requires an interaction between the measuring device and the system being measured. The device must be large enough and stable enough to register and record information, while the system being measured must be small enough and delicate enough to be influenced by the measurement. This creates an asymmetry that seems essential to the measurement process itself. Yet this asymmetry is puzzling when we remember that both the measuring device and the measured system are made of the same fundamental particles, obeying the same quantum laws. Why should some collections of particles behave as classical measuring devices, while others behave as quantum systems? The boundary between classical and quantum seems to be drawn by our perspective as observers rather than by any fundamental physical principle. This leads us to contemplate a possibility that makes many scientists uncomfortable. Perhaps the questions that reality can't answer aren't waiting for better theories or more sophisticated experiments. Perhaps they reveal something about the structure of inquiry itself, about the inherent limitations that exist whenever a part of reality tries to understand the whole. When we investigate the foundations of mathematics, we encounter a similar boundary. Kurt Gödel's incompleteness theorems demonstrate that any mathematical system powerful enough to describe arithmetic must contain statements that are true but cannot be proven within that system. This isn't a failure of mathematical reasoning, but a fundamental limitation of formal systems attempting to describe themselves completely. The parallel to physics is striking. Just as mathematics encounters statements that are true but unprovable, physics might encounter aspects of reality that are real but unmeasurable. The difference is that in mathematics, we can sometimes step outside the system and prove statements using a more powerful framework. In physics, there is no outside perspective. We are embedded within the reality we're trying to understand, using tools made of the same stuff we're investigating. This embeddedness creates profound difficulties for certain types of questions. When we ask about the nature of consciousness, we're using consciousness to investigate itself. When we ask about the foundations of physical law, we're using reasoning that presumably depends on those same laws. When we ask why there is something rather than nothing, we're using concepts that might only make sense because something exists. The question of consciousness illustrates this difficulty particularly clearly. We know with absolute certainty that conscious experience exists because we have direct access to it. Yet consciousness seems to resist every attempt at objective scientific explanation. We can map neural activity, identify the brain regions associated with different mental functions, and even predict some aspects of conscious experience based on neural states. But none of this explains why there should be any subjective experience at all. The philosopher David Chalmers has called this the hard problem of consciousness. Even if we could build a complete functional description of the brain, explaining every input, output, and computational process, it would still leave unexplained why these processes should feel like anything from the inside. The gap between objective description and subjective experience seems to persist no matter how detailed our scientific understanding becomes. Some researchers have suggested that consciousness might be fundamental to reality in ways we don't yet understand. They propose that subjective experience isn't produced by complex arrangements of unconscious matter, but is instead a basic feature of the universe, like mass or electric charge. This would mean that the hard problem of consciousness isn't waiting for a solution, but is actually pointing to a category error in how we've framed the question. Yet even this possibility raises new puzzles. If consciousness is fundamental, how does it interact with the physical world? How do subjective experiences influence objective events? The interaction problem that has plagued dualistic theories of mind doesn't disappear simply by making consciousness a basic feature of reality. It transforms into questions about how this fundamental consciousness manifests in the particular patterns we observe in brains and behaviour. These difficulties suggest that consciousness might represent a fundamental limit to scientific explanation, not because consciousness is mysterious or supernatural, but because the scientific method itself depends on the ability to separate observer from observed, subjective from objective. Consciousness is precisely the phenomenon that makes this separation problematic. The quantum measurement problem reveals a similar difficulty from the opposite direction. While consciousness seems to resist objective description, quantum mechanics suggests that objective description might itself be incomplete. The theory works perfectly for making predictions about measurement outcomes, but it doesn't tell us what happens between measurements, or even what constitutes a measurement in the first place. John Wheeler, one of the pioneers of quantum theory, proposed that we might need to abandon the idea of a universe that exists independently of observation. In his view, the universe is participatory, brought into existence through the act of observation itself. This doesn't mean that consciousness creates reality in some magical sense, but rather that the distinction between observer and observed might be an artifact of classical thinking that breaks down at the quantum level. Wheeler's participatory universe suggests that some questions might be unanswerable, not because they're too difficult, but because they assume a separation between questioner and reality that doesn't actually exist. When we ask what the universe was like before conscious observers evolved, we might be asking a question that assumes an impossible perspective, like asking what's north of the North Pole. The cosmological questions that keep physicists awake at night often have this same quality of assuming an impossible external perspective. When we ask why the universe exists rather than nothing, we're implicitly positioning ourselves outside of existence to contemplate the alternatives. But if we exist, we can't meaningfully occupy that external position. The question might be unanswerable, not because it's too profound, but because it's based on a conceptual confusion. Similarly, when we ask why the fundamental constants of physics have the particular values that allow for complexity in life, we might be asking a question that only makes sense from within a universe with those particular values. The anthropic principle suggests that we observe life-permitting constants precisely because we couldn't exist in a universe with different values. But this doesn't explain why any universe exists at all, or why the space of possible universes should be structured in a way that allows for observers like ourselves. The fine-tuning problem in cosmology illustrates how our most successful scientific theories can lead us to questions they cannot answer. The standard model of particle physics requires 19 parameters to be specified as input. These parameters, like the masses of fundamental particles and the strengths of fundamental forces, cannot be calculated from first principles. They must be measured experimentally and plugged into the theory. What's remarkable is how precisely these parameters must be tuned for a universe like ours to exist. If the strong nuclear force were slightly stronger, hydrogen nuclei would be too stable and stars couldn't burn. If it were slightly weaker, complex nuclei couldn't form and there would be no chemistry. Similar constraints apply to most of the other parameters. The range of values compatible with complexity appears to be extraordinarily narrow. Some physicists have proposed that our universe is just one member of a vast multiverse, with different regions having different values for the fundamental parameters. In such a scenario, we naturally find ourselves in a region with life-permitting values because we couldn't exist anywhere else. But the multiverse hypothesis raises its own unanswerable questions. How could we ever verify the existence of regions of reality that are by definition beyond our causal reach? And what determines the distribution of parameter values across the multiverse? The multiverse idea illustrates a recurring pattern in physics. When we encounter a question that seems to require an explanation, we often invent a larger theoretical framework that makes the original question seem natural or inevitable. But this typically pushes the mystery back one level rather than eliminating it. Why should there be a multiverse with the particular structure needed to solve the fine-tuning problem? Why should anything exist at all? These regress problems suggest that there might be irreducible features of reality that don't admit of further explanation. not because they're mystical or supernatural, but because explanation itself requires a framework of assumptions, and at some level, these assumptions cannot themselves be explained without circularity. The nature of mathematical truth presents a parallel puzzle. Mathematics seems to describe eternal, objective truths that exist independently of human minds. The fact that the square root of 2 is irrational doesn't depend on whether anyone believes it or has proven it. Yet mathematical truth also seems to require minds capable of grasping mathematical concepts. Numbers don't appear to exist in the same way that rocks and trees exist, yet they seem more certain and permanent than any physical object. Philosophers have debated for centuries whether mathematical objects like numbers and geometric shapes have an independent existence, or whether they're mental constructions that we project onto the world. Neither answer is entirely satisfactory. If mathematical objects exist independently, where do they exist and how do we gain knowledge of them? If they're mental constructions, why does mathematics work so well for describing the physical world? This question becomes even more puzzling when we consider that our most fundamental physical theories are mathematical in structure. General relativity describes gravity as the curvature of space-time, which is defined in terms of mathematical objects called tensors. Quantum mechanics describes the evolution of physical systems using complex vector spaces and linear operators. Are these mathematical structures discovering pre-existing features of reality, or are they imposing human conceptual frameworks onto a reality that might be fundamentally non-mathematical? The unreasonable effectiveness of mathematics in describing the natural world, as Eugene Wigner called it, suggests that there's some deep connection between mathematical truth and physical reality. Yet this connection remains mysterious. Why should the universe be mathematical at all? Why should creatures like ourselves, evolved for survival in a particular ecological niche, be capable of discovering mathematical truths that apply throughout the cosmos? These questions point to what might be the deepest puzzle of all: the relationship between mind and reality. Our minds appear to be products of a long evolutionary process, shaped by the need to survive and reproduce in a particular environment. Yet these same minds seem capable of grasping universal truths about logic, mathematics, and physical law that extend far beyond the ancestral environment in which they evolved. The capacity for abstract reasoning that allows us to understand quantum mechanics or general relativity seems vastly greater than what would have been needed for survival on the African savanna. How did evolution produce minds capable of understanding the structure of atoms or the expansion of the universe? This isn't just a question about the evolution of intelligence, but about the relationship between the particular and the universal, between the contingent processes that shaped our minds and the necessary truths they seem capable of discovering. If our minds are entirely products of evolution, shaped by the contingencies of natural selection, why should we trust them to reveal objective truths about reality? But if our minds have some special connection to universal truth, what is the nature of that connection, and how did it arise? The evolutionary debunking arguments in philosophy suggest that if our beliefs are entirely products of evolutionary processes aimed at survival rather than truth, we have no reason to believe they're actually true. Yet we seem to have escaped this trap, at least partially, through the development of science and mathematics. These disciplines have methods for correcting the biases and limitations of individual minds, allowing us to discover truths that no single person could have found alone. But this raises new questions about the relationship between individual minds and the collective enterprise of knowledge. Science works by creating communities of researchers who can check each other's work, replicate experiments, and build on previous discoveries. But what ensures that this collective process converges on truth, rather than just reinforcing shared delusions? The success of science in making accurate predictions and enabling new technologies suggests that it does track truth in some sense. Yet the history of science also shows how entire communities of researchers can be wrong about fundamental questions for centuries. The persistence of interpretational puzzles in quantum mechanics illustrates this difficulty. Nearly a century after the development of the theory, physicists still cannot agree on what it means despite its extraordinary empirical success. This suggests that empirical adequacy might not be sufficient to determine truth, at least for the deepest questions about the nature of reality. Perhaps reality has layers, and we've reached the point where the deeper layers are no longer accessible through the methods that worked for the surface layers. The classical physics that describes our everyday experience emerged from quantum mechanics through a process we don't fully understand. The living world emerged from the non-living world through a process we don't fully understand. Consciousness emerged from unconscious matter through a process we don't fully understand. Each emergence seems to involve the appearance of genuinely novel properties that cannot be reduced to or predicted from the underlying level. If emergence is a fundamental feature of reality, then there might be irreducible levels of description that cannot be unified into a single, complete theory. The dream of physics has been to find a final theory that explains everything in terms of a small number of fundamental principles. But perhaps this dream is based on a false assumption about the nature of explanation itself. And perhaps the most unsettling part is not that we don't have the answer, but that the question keeps surviving every explanation we invent. The boundary between what we can know and what we can measure has always been thinner than we'd like to admit. When you hold a coin and prepare to flip it, you assume the outcome is determined by forces you could, in principle, calculate. The angle of your thumb, the initial velocity, air resistance, the exact moment of release. Classical physics suggests that with enough precision, every coin flip becomes predictable. Yet when physicists push measurement to its ultimate limits, they discover something that undermines this entire picture. The more precisely you try to measure one aspect of reality, the more uncertain other aspects become. Not because your instruments are inadequate, but because uncertainty appears to be woven into the fabric of existence itself. This isn't merely a technical inconvenience. It points to something far more fundamental about the relationship between knowledge and reality. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we pin down where something is, the less we can know about where it's going. This trade-off isn't a limitation of our measuring devices or a temporary gap in our understanding. It's a mathematical necessity that emerges from the quantum description of nature itself. But the uncertainty principle reveals only the surface of a much deeper puzzle. Every measurement requires an interaction between the measuring device and the system being measured. The device must absorb or emit energy to register information about the system. This interaction inevitably disturbs the system, changing the very properties we're trying to measure. In the classical world, we imagine we can make these disturbances arbitrarily small by building more sensitive instruments. In the quantum world, there's a minimum disturbance that can never be eliminated. This creates a peculiar situation. The act of measurement, which we think of as revealing pre-existing properties of reality, actually appears to participate in creating those properties. Before measurement, quantum theory suggests that particles don't have definite positions or momenta at all. They exist in what physicists call superpositions, ghostly combinations of all possible states. The measurement doesn't just reveal which state the particle was in. It forces the particle to choose a definite state from among the possibilities. Consider what this means for our understanding of objectivity. Science has traditionally been built on the assumption that there's a clear distinction between the observer and the observed, between the knower and the known. We study reality by stepping outside it, at least conceptually, and examining it with detached objectivity. But quantum mechanics suggests that this separation might be impossible to maintain. The observer and the observed become entangled in ways that make it meaningless to talk about either one independently. The mathematics of quantum mechanics has been tested with extraordinary precision for nearly a century. It predicts the behavior of atoms, molecules, and subatomic particles with an accuracy that exceeds almost any other scientific theory. Technologies from lasers to computer chips depend on our quantum understanding of matter and energy. Yet despite this practical success, physicists still cannot agree on what the theory actually tells us about the nature of reality. Some interpretations suggest that multiple versions of reality coexist simultaneously, branching and splitting with every quantum measurement. Others propose that reality remains fundamentally uncertain until conscious observers collapse the quantum possibilities into definite outcomes. Still others maintain that there's a deeper, hidden reality beneath the quantum description, governed by variables we cannot directly observe. Each interpretation addresses some puzzling aspects of quantum mechanics, while introducing new conceptual difficulties. The many worlds interpretation eliminates the mysterious collapse of quantum states by suggesting that all possible outcomes actually occur in parallel realities. But this solution comes at the cost of populating the universe with an infinite number of unobservable worlds. The hidden variable theories preserve the idea of objective reality by proposing that particles always have definite properties, even when we can't measure them. But these theories require accepting instantaneous influences between distant particles, violating our intuitions about causality and locality. The persistence of these interpretational puzzles reveals something profound about the limits of scientific explanation. We have a theory that works with unprecedented precision, yet we cannot determine what it means. The gap between mathematical formalism and physical understanding remains as wide today as it was when quantum mechanics was first developed. This situation becomes even more perplexing when we consider the role of information in quantum theory. John Wheeler, one of the pioneers of quantum physics, proposed that information might be more fundamental than matter or energy. In his view, physical reality emerges from the answers to yes or no questions asked of quantum systems. Every measurement can be seen as asking nature a binary question. Is the particle here or there? Is the spin up or down? Reality, in this picture, is built from bits of information rather than chunks of matter. If Wheeler's intuition is correct, then the boundary between physical and informational reality becomes blurred. The question of what exists independently of measurement becomes meaningless because measurement is the process by which existence itself is defined. This doesn't mean that consciousness creates reality in some mystical sense, but rather that the distinction between objective and subjective might be an artifact of classical thinking that breaks down at the quantum level. The implications extend far beyond physics into questions about the nature of knowledge itself. If reality is fundamentally informational, then the process of gaining knowledge about the world becomes a process of participating in its creation. The questions we ask and the measurements we perform don't just reveal pre-existing facts. They help determine what facts exist to be revealed. This participatory view of reality challenges our most basic assumptions about the relationship between mind and world. We typically think of knowledge as a passive reflection of external reality in our minds. But if observation plays an active role in determining the properties of physical systems, then knowledge becomes a creative act that shapes the world even as it describes it. The measurement problem in quantum mechanics illustrates this difficulty with particular clarity. When we measure a quantum system, we seem to cause its superposition of possibilities to collapse into a single, definite outcome. But what counts as a measurement? Does it require a conscious observer, or can any interaction between quantum systems trigger the collapse? The theory itself provides no clear answer to this question. Some physicists have suggested that consciousness might play a role in quantum measurement, though this remains highly speculative and is not part of the standard formalism. The idea is that subjective awareness is what transforms quantum possibilities into classical realities. But this proposal raises as many questions as it answers. What exactly constitutes consciousness? Does a mouse collapse quantum states? What about a computer or a bacterium? And if consciousness is required for measurement, how do we explain the existence of a classical world before conscious observers evolved? The alternative is to accept that the collapse of quantum superpositions doesn't require consciousness at all, but occurs whenever quantum systems become entangled with their environment. This process, called decoherence, explains why we don't observe macroscopic superpositions in everyday life. The delicate quantum coherence that allows particles to exist in multiple states simultaneously is rapidly destroyed by interactions with surrounding particles. But decoherence alone doesn't solve the measurement problem. It explains why quantum superpositions become unobservable in practice, but it doesn't explain why measurements yield definite outcomes rather than leaving us with an entangled combination of all possibilities. The mathematics of decoherence still describes a world where all possible measurement outcomes coexist, even if they're hidden from our direct observation. This brings us to one of the most unsettling implications of quantum mechanics. If the theory is taken at face value, without additional assumptions about consciousness or hidden variables, it suggests that reality might be fundamentally observer-dependent. Different observers, making different measurements at different times, might experience genuinely different realities. What we take to be objective facts about the world might actually be features of our particular measurement interactions. The idea of observer-dependent reality seems to violate everything we think we know about the nature of science. Scientific knowledge has traditionally been valued precisely because it transcends individual perspectives and reveals universal truths about objective reality. But quantum mechanics suggests that the observer cannot be eliminated from the description of physical systems. The properties we measure are not intrinsic features of the systems themselves, but emerge from the relationship between observer and observed. This doesn't mean that science becomes subjective in the sense that anything goes or that all perspectives are equally valid. Quantum mechanics makes precise, testable predictions about the probabilities of different measurement outcomes. But it suggests that these probabilities might be all there is to know about reality. The idea of a deeper, objective reality beneath the quantum description might be a conceptual mistake. The tension between quantum mechanics and our classical intuitions about reality becomes even more apparent when we consider the phenomenon of quantum entanglement. When two particles become entangled, measuring one particle instantaneously affects the properties of the other, regardless of how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate the principle that influences cannot travel faster than light. Einstein, along with colleagues Podolsky and Rosen, argued that quantum entanglement demonstrated the incompleteness of quantum theory. They proposed that particles must have predetermined properties, hidden from direct observation, that account for the correlations we observe between distant measurements. This would preserve the idea of objective reality while explaining the strange predictions of quantum mechanics. But subsequent experiments have consistently confirmed the quantum predictions and ruled out the hidden variable theories proposed by Einstein and others. The correlations between entangled particles are stronger than any classical theory can explain. Nature seems to violate what physicists call local realism, the combination of the ideas that objects have definite properties independent of observation and that influences cannot travel faster than light. The violation of local realism forces us to choose between two equally unsettling possibilities. Either objects don't have definite properties independent of measurement, or influences can travel instantaneously across any distance. Most physicists accept the first alternative, abandoning objective reality in favor of preserving the speed of light as a universal limit. But this choice comes at the cost of undermining our most basic assumptions about the nature of physical existence. The philosophical implications of quantum mechanics become even more puzzling when we consider recent experiments that push the boundaries of quantum behavior. Physicists have succeeded in creating quantum superpositions of increasingly large and complex systems. Individual atoms, small molecules, even tiny mechanical oscillators have been coaxed into existing in multiple states simultaneously. These experiments suggest that there may be no fundamental limit to quantum effects, no natural boundary where the quantum world gives way to the classical world of everyday experience. Yet somewhere in the transition from microscopic to macroscopic, quantum strangeness seems to disappear. The superpositions that are commonplace in the atomic world become vanishingly rare in the world of cats and chairs and measuring devices. Understanding this transition, called the quantum to classical boundary, remains one of the central challenges in physics. The persistence of the measurement problem, nearly a century after the development of quantum mechanics, suggests that we might be encountering a fundamental limit to scientific explanation. Not because the phenomena are too complex or the mathematics too difficult, but because the very nature of measurement and observation might be irreducibly mysterious. Consider the act of measurement itself. Every measuring device must be large enough and stable enough to register and record information, while the system being measured must be small enough and delicate enough to be influenced by the measurement. This creates an asymmetry that seems essential to the measurement process. But this asymmetry is puzzling when we remember that both the measuring device and the measured system are made of the same fundamental particles, obeying the same quantum laws. Why should some collections of particles behave as classical measuring devices, while others behave as quantum systems? The boundary between classical and quantum seems to be drawn by our perspective as observers rather than by any fundamental physical principle. This suggests that the measurement problem might not be a problem with quantum mechanics, but rather a reflection of the inherent limitations that arise when a part of reality tries to understand the whole. The parallel to Gödel's incompleteness theorems in mathematics is striking. Gödel showed that any mathematical system powerful enough to describe arithmetic must contain statements that are true but cannot be proven within that system. This isn't a failure of mathematical reasoning, but a fundamental limitation of formal systems attempting to describe themselves completely. Perhaps physics encounters a similar limitation when it tries to provide a complete description of the measurement process. In mathematics, we can sometimes step outside a system and prove statements that are unprovable within it by using a more powerful framework. In physics, there may be no outside perspective available. We are embedded within the reality we're trying to understand, using tools and concepts that are themselves part of that reality. The questions we ask about the foundations of physics must be formulated using the very concepts and assumptions that we're trying to examine. This embeddedness creates profound difficulties for certain types of questions. When we ask about the nature of measurement, we're using concepts that presuppose the possibility of measurement. When we ask about the relationship between observer and observed, we're adopting the perspective of observers. When we ask about the foundations of physical law, we're using reasoning that presumably depends on those same laws. The measurement problem in quantum mechanics might be unanswerable, not because it's too difficult, but because it represents a question that reality cannot coherently pose about itself. The very act of asking about measurement presupposes the existence of observers capable of making measurements, but the theory we use to understand measurement suggests that the properties of observers and observed systems become entangled in ways that resist clear separation. This possibility is both intellectually humbling and strangely liberating. It suggests that some questions might persist, not because we haven't found the right answers, but because the questions themselves exist at the boundary where inquiry becomes impossible. The measurement problem survives every proposed solution, not because the solutions are inadequate, but because the problem itself might be pointing to the limits of what any physical theory can coherently describe. If this interpretation is correct, then the measurement problem joins a small but significant class of questions that appear to be fundamentally unanswerable. These are not questions waiting for better theories or more sophisticated experiments. They are questions that reveal something about the structure of inquiry itself, about the inherent limitations that exist whenever a part of reality attempts to provide a complete account of the whole. The persistence of the measurement problem, its resistance to resolution despite decades of theoretical and experimental progress, suggests that we might be encountering one of these fundamental boundaries. Not a boundary imposed by our current ignorance or technological limitations, but a boundary that emerges from the very nature of measurement and observation. And perhaps the most unsettling part is not that we don't have the answer, but that this particular question seems to reconstruct itself within every framework we build to escape it. The questions that resist our best attempts at understanding seem to cluster around the edges of what we can actually measure. Consider time itself. You experience it as a flowing river, carrying you from past through present toward future. This feeling is so immediate, so undeniable, that questioning it feels almost absurd. Yet when physicists write down their most fundamental equations describing the behavior of particles, forces and fields, something peculiar emerges. Time appears in these equations not as a flowing quantity, but as just another coordinate, like length or width. The mathematics suggests that all moments, past, present and future, exist with equal reality, laid out in what physicists call a block universe. This creates a strange situation. The subjective experience that seems most certain to you, the flowing of time, appears to be absent from the objective description that works best for predicting how the universe behaves. Either your direct experience is systematically misleading you about the nature of temporal reality, or our most successful physical theories are missing something essential about how time actually works. Both possibilities are uncomfortable, but the tension between them points to something deeper than a simple misunderstanding. The block universe isn't merely a philosophical curiosity. Einstein's theory of relativity demonstrates that simultaneity is relative. Two observers moving at different speeds will disagree about which events are happening now. If there were a universal present moment that divides past from future, these observers should be able to identify it, but they can't. What one observer considers simultaneous events, another observer sees as sequential. The mathematics forces us to conclude that all moments in time must be equally real, existing together in a four-dimensional structure. Yet this mathematical conclusion conflicts with something even more fundamental than our experience of temporal flow. It conflicts with our understanding of causation itself. If all moments are equally real, then the future already exists, complete and determined. But causation seems to require that causes precede their effects, that events unfold through time rather than being timelessly arranged. The tension between the block universe and our causal understanding of reality reveals a puzzle that neither physics nor philosophy has managed to resolve. This puzzle becomes more acute when we consider the role of the second law of thermodynamics. This law states that entropy, roughly speaking, the amount of disorder in a system, always increases over time. A hot cup of coffee cools down, but we never observe a cold cup spontaneously heating up by absorbing thermal energy from the surrounding air. Breaking eggs scatter their contents, but scattered contents never spontaneously reassemble into whole eggs. The second law explains why we remember the past but not the future, why causes seem to precede effects, why time appears to have a direction. But the second law is statistical rather than absolute. It describes the overwhelmingly likely behavior of systems containing many particles, but it doesn't forbid the occasional violation. A cold cup of coffee could, in principle, spontaneously warm up if all the surrounding air molecules happen to transfer their kinetic energy to the coffee at the same time moment. The probability of this occurring is so vanishingly small that we never observe it, but the mathematical possibility remains. This statistical nature of the second law raises uncomfortable questions about the arrow of time. If the fundamental laws of physics are symmetric with respect to time, treating past and future equally, then where does the apparent direction of time come from? The second law provides a partial answer by showing how statistical tendencies can create an apparent arrow pointing toward increasing disorder. But this explanation depends on the assumption that the universe began in a state of unusually low entropy, a condition that itself requires explanation. The initial low entropy of the universe seems to require an extraordinary degree of fine-tuning. Roger Penrose has calculated that the probability of the universe beginning with entropy low enough to account for the second law is approximately 1 part in 10 to the power of 10 to the power of 123. This number is so large that it's difficult to comprehend. It's vastly larger than the number of particles in the observable universe, vastly larger than the number of possible quantum states that could fit within the universe. The precision required seems to exceed anything we might reasonably attribute to chance. Yet without this initial condition, the second law wouldn't operate as we observe it, and the universe would lack the thermodynamic arrow of time that seems to underlie our experience of temporal flow. The question of why the universe should have begun in such an improbable state remains one of the deepest puzzles in cosmology. Some physicists have proposed that our universe is just one member of an infinite multiverse, and we naturally find ourselves in a member with low initial entropy because we couldn't exist in universes with high initial entropy. But this explanation pushes the mystery back one level without resolving it. The puzzle of time connects to another fundamental question that physics cannot answer: why the universe appears to be governed by mathematical laws at all. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. Mathematical concepts developed for purely abstract reasons often turn out to describe physical phenomena with extraordinary precision. Complex numbers, originally invented to solve algebraic equations, became essential for quantum mechanics. Riemannian geometry, developed as an exercise in pure mathematics, became the language of general relativity. This effectiveness of mathematics seems to go far beyond what we might expect from evolutionary considerations. Our brains evolved to help us survive and reproduce in a particular ecological niche. The cognitive abilities that allowed our ancestors to track animals, gather plants, and navigate landscapes seem very different from the abilities required to understand quantum field theory or general relativity. Yet somehow, the same neural structures that guided survival on the African savanna also enable us to comprehend the structure of atoms and the expansion of the universe. The mystery deepens when we consider that mathematical truths seem to exist independently of human minds. The fact that the sum of angles in a triangle equals 180 degrees doesn't depend on whether anyone has discovered or proven this fact. Mathematical objects like numbers and geometric shapes appear to have a kind of eternal existence that transcends the physical world. Yet they also seem to require minds capable of grasping mathematical concepts. Numbers don't exist in the same way that rocks and trees exist, yet they seem more permanent and certain than any physical object. This raises profound questions about the relationship between mathematical truth and physical reality. Are the mathematical structures that appear in our physical theories discovering pre-existing features of reality, or are they imposing human conceptual frameworks onto a reality that might be fundamentally non-mathematical? If mathematical objects exist independently of human minds, where do they exist and how do we gain access to them? If they are mental constructions, why do they work so well for describing the behaviour of electrons and galaxies? The puzzle becomes even more perplexing when we consider that our most fundamental physical theories suggest that reality might be informational rather than material in nature. Quantum mechanics describes particles not as tiny objects with definite properties, but as probability distributions, mathematical entities that encode information about possible measurement outcomes. John Wheeler proposed that physical reality might emerge from the answers to binary questions asked of quantum systems. In his memorable phrase, "it from bit," he suggested that information might be more fundamental than matter or energy. If Wheeler's intuition is correct, then the boundary between mathematical and physical reality becomes blurred. The equations that describe quantum systems wouldn't be approximations or representations of some underlying material reality. They would be the reality itself, mathematical structures that somehow give rise to the experience of a physical world. This possibility is both elegant and deeply unsettling. It suggests that the solid world of everyday experience might be a kind of illusion, a user interface that conceals the abstract informational processes operating beneath the surface. The informational interpretation of quantum mechanics connects to another persistent puzzle, the measurement problem. Quantum theory describes particles as existing in superpositions of multiple states simultaneously until they are measured. A particle can be in multiple locations at once, spinning in multiple directions, having multiple energies. But the moment someone or something measures the particle, this superposition collapses and the particle acquires definite properties. The mathematics of quantum mechanics predicts the probabilities of different measurement outcomes with extraordinary accuracy. Technologies from lasers to computer processors depend on our quantum understanding of matter and energy. Yet despite this practical success, physicists cannot agree on what happens during the measurement process itself. The theory tells us what we will observe, but it doesn't tell us why observation should cause superpositions to collapse, or even what constitutes an observation in the first place. Some interpretations suggest that consciousness plays a special role in quantum measurement. The idea is that subjective awareness is what transforms quantum possibilities into classical realities. But this proposal raises as many questions as it answers. What exactly constitutes consciousness? Does a mouse collapse quantum states? What about a computer or a bacterium? And if consciousness is required for measurement, how do we explain the existence of a classical world before conscious observers evolved? Other interpretations attempt to avoid the measurement problem entirely. The many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur but in separate parallel universes. When you measure a particle's position, the universe splits into multiple branches, each containing a different outcome. You experience only one branch, but all the others exist just as real as yours. This interpretation preserves the mathematics of quantum mechanics without requiring any mysterious collapse, but at the cost of populating reality with an infinite number of unobservable parallel worlds. Yes, the pilot wave theory takes a different approach, proposing that particles always have definite positions and momenta, but they're guided by a quantum field that we cannot directly observe. This hidden reality determines the outcomes of measurements while preserving the probabilistic predictions of quantum mechanics. Yet this interpretation requires accepting instantaneous influences across vast distances and abandoning the principle that physics should only deal with observable quantities. Each interpretation addresses some aspects of the measurement problem while introducing new conceptual difficulties. The persistence of fundamental disagreement among physicists reveals something profound about the limits of empirical investigation. We have a theory that works with unprecedented precision for making predictions about measurement outcomes, yet we cannot determine what it tells us about the nature of reality itself. The measurement problem becomes even more acute when we consider recent experiments that demonstrate quantum effects in increasingly large systems. Physicists have created quantum superpositions of individual atoms, small molecules, even tiny mechanical oscillators. These experiments push the boundary between quantum and classical behavior, but they don't resolve the fundamental question of where that boundary lies or why it should exist at all. The process of decoherence explains why quantum superpositions become unobservable in macroscopic systems. When a quantum system becomes entangled with its environment, the delicate coherence that allows for superpositions is rapidly destroyed by interactions with surrounding particles. This explains why we don't observe cats existing in superpositions of alive and dead states, but it doesn't explain why measurements yield definite outcomes rather than leaving us with an entangled combination of all possibilities. If you pause and really sit with this puzzle, it reveals something unsettling about the relationship between theory and reality. Quantum mechanics works perfectly for predicting what we will observe, but it seems to require that we already know what constitutes an observation before we can apply it. The theory presupposes the existence of classical measuring devices and conscious observers, but it cannot explain how such classical entities emerge from the quantum substrate that presumably underlies everything. This circularity suggests that quantum mechanics might be incomplete in a fundamental way, not incomplete in the sense that it makes wrong predictions, but incomplete in the sense that it cannot provide a self-contained description of the physical world. The theory works by dividing reality into a quantum system being observed and a classical apparatus doing the observing, but it cannot explain where this division comes from or why it should exist. The measurement problem connects to broader questions about the role of observation in physical theory. Science has traditionally been built on the assumption that there's a clear distinction between the observer and the observed, between the knower and the known. We study reality by stepping outside it, at least conceptually, and examining it with detached objectivity. But quantum mechanics suggests that this separation might be impossible to maintain at the most fundamental level. The observer and the observed become entangled in ways that make it meaningless to talk about either one independently. The properties we measure are not intrinsic features of quantum systems, but emerge from the relationship between the system and the measuring apparatus. This doesn't mean that quantum mechanics is subjective in the sense that different observers can get different results from the same measurement. The theory makes precise, objective predictions about measurement probabilities, but it suggests that these probabilities might be all there is to know about quantum reality. The idea that reality might be fundamentally relational rather than consisting of objects with intrinsic properties challenges our most basic assumptions about the nature of existence. We typically think of the world as composed of things that have properties whether or not anyone observes them. A rock has a definite mass and location, even when no one is measuring it. But quantum mechanics suggests that this assumption might be wrong, at least for microscopic systems. The puzzle becomes even more perplexing when we consider that macroscopic objects, like rocks, are made entirely of quantum particles. If individual particles don't have definite properties independent of measurement, how do collections of such particles give rise to objects that seem to have definite properties? The transition from quantum to classical remains one of the deepest mysteries in physics. Some physicists have suggested that the classical world emerges through a process of decoherence, where quantum superpositions become so entangled with their environment that they effectively behave like classical systems. But decoherence alone doesn't solve the measurement problem. It explains why quantum effects become unobservable in practice, but it doesn't explain why measurements have definite outcomes rather than leaving us with quantum superpositions of different measurement results. The persistence of the measurement problem, nearly a century after the development of quantum mechanics, suggests that we might be encountering a fundamental limit to physical explanation. Not because the mathematics is too difficult or the experiments too complex, but because the very concepts of measurement and observation might be irreducibly mysterious. Consider what happens when we try to give a complete physical description of a measurement. The measuring device must be large enough and stable enough to register information about the quantum system. But the device itself is made of quantum particles that presumably obey the same laws as the system being measured. Why should some collections of quantum particles behave as classical measuring devices, while others behave as quantum systems? The boundary between classical and quantum seems to be drawn by our perspective as observers rather than by any fundamental physical principle. We treat some systems as classical because we cannot or do not observe their quantum properties, not because they actually lack such properties. This suggests that the measurement problem might not be a problem with quantum mechanics itself, but rather a reflection of the inherent limitations that arise when a part of reality tries to provide a complete description of the whole. The parallel to Gödel's incompleteness theorems is striking. Gödel showed that any mathematical system powerful enough to describe arithmetic must contain statements that are true but cannot be proven within that system. This isn't a failure of mathematical reasoning, but a fundamental limitation of formal systems attempting to describe themselves completely. Perhaps physics encounters a similar limitation when it tries to provide a complete description of the measurement process. In mathematics, we can sometimes step outside a system and prove statements that are unprovable within it by using a more powerful framework. In physics, there may be no outside perspective available. We are embedded within the reality we're trying to understand, using instruments and concepts that are themselves part of that reality. The questions we ask about measurement must be formulated using the very concepts that presuppose the possibility of measurement. This embeddedness creates profound difficulties for understanding the foundations of physics. When we ask about the nature of measurement, we're using concepts that assume the existence of observers capable of making measurements. When we ask about the relationship between observer and observed, we're adopting the perspective of observers. The circularity seems inescapable. The measurement problem might be unanswerable, not because it's too difficult, but because it represents a question that reality cannot coherently ask about itself. The very act of formulating the problem presupposes the existence of the classical world of observers and measuring devices, but the quantum theory we use to understand measurement suggests that this classical world emerges in ways that resist clear explanation. This possibility is both intellectually humbling and strangely liberating. It suggests that some questions might persist, not because we haven't found the right answers, but because the questions themselves exist at the boundary where systematic inquiry becomes impossible. The measurement problem survives every proposed solution, not because the solutions are inadequate, but because the problem might be pointing to the limits of what any physical theory can coherently describe. If this interpretation is correct, then the measurement problem joins a small but significant class of questions that appear to be fundamentally unanswerable within the frameworks that generate them. These are not questions waiting for better theories or more sophisticated experiments. They're questions that reveal something about the structure of inquiry itself, about the inherent limitations that exist whenever a part of reality attempts to provide a complete account of the whole. The persistence of the measurement problem, its resistance to resolution despite decades of theoretical and experimental progress, suggests that we might be encountering one of these fundamental boundaries. Not a boundary imposed by our current ignorance or technological limitations, but a boundary that emerges from the very nature of measurement and observation. And perhaps the most unsettling part is not that we don't have the answer, but that this particular question seems to reconstruct itself within every framework we build to escape it. This circle of explanation reveals something profound about the nature of inquiry itself. Every time we think we've found solid ground. Every time we believe we've identified the fundamental level of reality, we discover that our explanation depends on concepts and assumptions that themselves require explanation. The measuring devices we use to probe quantum systems are made of quantum particles. The mathematical frameworks we use to describe physical laws emerge from minds that are themselves physical systems. The logic we use to analyze the foundations of knowledge operates according to principles that we cannot justify without using that same logic. This isn't merely a technical problem waiting for a more clever solution. It points to something deeper about what it means for a part of reality to understand the whole. When consciousness tries to understand consciousness, when measurement tries to understand measurement, when existence tries to understand existence, we encounter a kind of conceptual vertigo that no amount of additional data seems able to resolve. Consider what happens when we try to answer the most basic question of all. Why does anything exist rather than nothing? This question seems to demand an ultimate explanation, a final reason that would make existence necessary rather than contingent. But every answer we might offer presupposes the existence of something, whether logical principles, causal mechanisms, or mathematical truths. To explain why there is something, we must invoke something else, and that something else requires its own explanation. The philosopher Gottfried Leibniz called this the principle of sufficient reason. Everything that exists must have a reason for existing. But when we apply this principle to existence itself, we create an infinite regress. Each reason requires a further reason. Each explanation demands a deeper explanation. We cannot bootstrap existence from nothingness using purely logical arguments, because logic itself seems to require some form of existence to operate. Some philosophers have argued that this question is meaningless, that it arises from a confusion about the nature of existence itself. They suggest that existence is not a property that things can have or lack, but rather the fundamental condition that makes properties possible at all. To ask why there is something rather than nothing, in this view, is like asking why truth is true or why logic is logical. The question assumes a perspective outside existence that we cannot coherently occupy. But the persistence of this question across cultures and centuries suggests that it captures something important about the human encounter with reality. Even if the question is ultimately unanswerable, the fact that we can ask it reveals something remarkable about our position in the cosmos. We are arrangements of matter that have become aware of their own existence, patterns in the universal flux that can contemplate the mystery of their own being. This capacity for self-reflection creates its own puzzles. How did unconscious matter give rise to conscious experience? How did meaningless physical processes generate minds capable of grasping meaning? The emergence of consciousness from non-conscious matter seems to require a kind of explanatory leap that our scientific frameworks struggle to accommodate. The hard problems of consciousness, as philosophers call it, illustrates this difficulty with particular clarity. We can map every neural pathway in the brain, identify the patterns of activity associated with different mental states, even predict some aspects of conscious experience based on brain imaging data. But none of this explains why there should be any subjective experience at all. The gap between objective neural activity and subjective conscious experience seems to persist no matter how detailed our scientific understanding becomes. Some researchers have proposed that consciousness might be a fundamental feature of reality, like mass or electric charge, rather than something that emerges from complex arrangements of unconscious matter. This panpsychist view suggests that subjective experience exists at some level in all physical systems, and that the rich consciousness we associate with human minds represents a particularly sophisticated integration of more basic conscious elements. But even this radical proposal doesn't eliminate the mystery. If consciousness is fundamental, how does it interact with the physical world? How do subjective experiences influence objective events? The interaction problem that has plagued dualistic theories of mind doesn't disappear simply by making consciousness a basic feature of reality. It transforms into questions about how this fundamental consciousness manifests in the particular patterns we observe in brains and behavior. The relationship between consciousness and quantum mechanics adds another layer to this puzzle. Some physicists have suggested that consciousness might play a special role in the collapse of quantum superpositions, that subjective awareness is what transforms quantum possibilities into classical realities. But this proposal raises as many questions as it answers. What constitutes consciousness for the purposes of quantum collapse? Does a sophisticated computer system collapse quantum states? What about a simple thermostat that responds to environmental changes? The boundaries we draw around consciousness seem arbitrary when viewed from the perspective of physics. Every system responds to its environment in ways that could be described as forms of measurement or information processing. A rock registers the impact of raindrops. A plant tracks the movement of the sun. A virus responds to the chemical environment of a host cell. If consciousness is defined by the ability to respond to and integrate information, then it might be far more widespread than we typically assume. Perhaps the deepest unsettling truth is not that we've encountered questions beyond our current understanding, but that we've discovered questions that seem to exist beyond the reach of understanding itself. The measurement problem persists, not because quantum mechanics is wrong, but because it might be pointing to something more fundamental about the relationship between knowledge and reality. When a part tries to understand the whole, when consciousness attempts to grasp the nature of consciousness. When measurement seeks to explain measurement, we encounter boundaries that may not be temporary obstacles, but permanent features of the terrain. The circularity isn't a bug in our reasoning. It might be an unavoidable consequence of our embedded position within the reality we're trying to comprehend. This doesn't diminish the remarkable achievements of science, or suggest that inquiry should cease. The technologies that emerge from quantum mechanics work precisely because we can predict measurement outcomes with extraordinary accuracy. But it does suggest that certain questions might remain perpetually open, not as failures of human ingenuity, but as windows into the fundamental structure of inquiry itself. The question that our current frameworks cannot fully answer might not be waiting for a better theory or a more sophisticated experiment. It might be the question that emerges whenever any system complex enough to ask questions encounters the limits of what questions can coherently mean. And perhaps the most profound discovery is not that we don't have the answer, but that some questions exist in the space between the questioner and the questioned, where no answer could ever be complete. If questions like this tend to linger with you rather than resolve neatly, this channel exists for that kind of curiosity.